Okay, class, here we are back for the second half of the economics of absorption cooling presentation. This is the slide that we finished up on the part one, so I will move on here. And so here we go. So we're going to do an example located in Washington, D.C. With 1,000 tons of load, and we have two chillers. We have a 400-ton direct fired absorber where the COP listed at 1.01, and the other is a 600-ton electric centrifugal at 0.6 kW per ton, and I think we calculated that last time. That's I think it was 5.86 was the COP on that guy. Design conditions are for 42-degree water leaving the chiller and 85-degree condenser water, cooling tower water coming in that's the cold temperature coming out of the cooling tower supplied to the chiller. Our natural gas cost is 45 cents a therm, and a therm is 100,000 BTUs, 10 therms to a million. Washington, D.C. electrical rate structure, which I think we talked about a little bit before, or we had calculated the cost of operating the centrifugal on load. Well, the example was for on load, but then they went through and have a cost for each of the periods of the day. This shows the overall building load profile. So you see the very top of these curves right through here. Goodness, excuse me. Up to the top, that's the total load on the building as a function of hour of day. And this is during the summertime, where this is the on-peak period. Well, the on-peak period is noon to 8 over here. And so we're going to run the absorber from 8 a.m. until 8 p.m. But it's going to be fully loaded for all of the on-peak. When there's more load than that, and then when the load falls off, obviously we won't have to produce as much refrigeration. But the blue here is the amount of the load that the absorber is going to provide, and the overall peaks here are the total cooling load. Okay, so the results show that the direct fired absorption system saves approximately $27,000 a year in operating cost. Lower cooling tower flows can decrease the installed cost while improving system efficiency. We'll see that some of the more recent chillers, especially Train is talking about theirs, can reduce condenser water flow from the typical 4.5 GPM per ton for this type of absorber down to about 3.6 GPM per ton, which then means you don't have to buy as big of pumps and maybe pipe size down a little bit and this, that, and the other. Maintenance costs with new direct fired absorption are as low, in some cases lower than centrifugals. It surprises me a little, but I trust them. I trust that's good information. And again, they've used the TRACE program to quantify the numbers, or provide the numbers in this study. Okay, so that is the motivation. Then the question is, how much extra am I going to have to spend in order to, instead of just going straight centrifugal, in order to get this $27,000 a year in savings? So any place that has this type of rate structure, there would be potential for these hybrid chill water plants. Okay, now we wind up with, there's a number of slides about advances in technology, and then they have some example simulation, some data from the simulations to talk about. Okay, so here's kind of a long drawn out history of this stuff. Single stage absorption became popular in the 50s. Train entered the market in 59. Carrier doing this commercially in the 40s. Early 70s, Train was the first to introduce a two-stage steam unit. At this point, absorption comprised close to 30% of the large chiller market. But in the 70s, the oil embargo came, fossil fuel prices went up significantly, and so these things fell in popularity because it was so expensive to operate them. During the 70s, Train was the only manufacturer to stay in the absorption market. All other domestic manufacturers got out of business due to you just couldn't sell them. Through the 70s and 80s, Japanese market for absorption increased. So Japanese manufacturer jumped in and began to further develop the technology. In the late 80s, Japanese manufacturers began to export to the U.S., and all domestic chiller manufacturers teamed up with Japanese companies to bring the product to the U.S. Introduction of microprocessor controls in the 1990s began to change the face of absorption chillers. Microcontrols were able to eliminate many problems that had plagued absorption for over the years. Currently, several domestic manufacturers are manufacturing Japanese design units in U.S., Mexico. Train took another route and they completely redesigned its entire product line of absorption to include single stage, direct fired, and two-stage steam. This redesigned product was introduced in 1995. Okay, so these are the problems. We've been through crystallization, power loss, and air and machine. So those are the causes of crystallization, so we don't have to go back through those. Slow response, we'll hit that and then talk about a little bit more here. Let's see. Okay, so all absorbers have traditionally been slow reacting to any changes in system load. If load increases rapidly, cooling tower temperature drops, or those are examples, can take the absorption chiller a long time to react properly. Absorption cycle works like a thermal flywheel. As heat is input through the steam valve or burner, it takes a lot of time for the heat input to make its way through the cycle that produces chill water. So changes in heat input take a while to be reflected in the output. And that's traditionally been the problem. Difficult to operate and maintain. Operators have gained a reputation for requiring extensive attention. Some reasons for this were purging requirement were manual and had to be done daily or weekly. The lack of trained service personnel was an issue, and so in general they've not had a great reputation over the past 40, 50 years. Corrosion is another problem we've talked about a little bit with lithium bromide. The salt is very corrosive to standard metals. Okay, so what are solutions to some of these problems? Well, controls, materials, and some added features. A lot of these problems are pretty much things of the past. Okay, so one big addition is variable use of variable frequency drives on the pumps. It improves part load efficiency, improves response time, and allows for low part load operation. One of the most critical elements in developing a chiller that can handle a variety of conditions is to address the thermal flywheel effect within the absorption cycle. This is accomplished by providing VFDs on solution pumps. VFDs have the capability of short-circuiting this thermal flywheel to provide an almost instantaneous response to changing load. Another side benefit of VFDs is that they improve part load efficiency. We're now able to run part load down to about 12%. So it has an 8-to-1 turn down, which is really impressive and significant on steam and direct fired. Since we now have the ability to fully modulate the machine, its burner down to 12%, we save on maintenance because we're not cycling the burners on and off as much as they used to. they claim other manufacturers can only modulate down to 30%. These slides are probably a little bit dated, so I'm not sure if that's still true or not. That would take some market research to figure out. We have also solved the problem of crystallization on power shutdowns by using a combination of normally open valves on the unit. Upon power loss, the unit goes into a gravity-fed dilution cycle that will prevent the unit from crystallizing even with a total power loss. And so you don't need auxiliary power. Power is restored, the unit will automatically reset itself and begin to produce chill water. Low chilled water temperature. So traditionally, about 42 degrees was as low as the absorber could go. Now, primarily because of microprocessor, microelectronic controls, we can produce chill water down to 40 or even lower. This capability can be good for indoor air quality and retrofit applications. Direct fire absorbers have the capability to produce hot water up to 180 degrees. We mentioned that previously. With the use of a heat exchanger, the unit can produce hot water and chill water simultaneously and can be set to run in a heating preference mode or a cooling preference mode. So that's pretty nice. Changeover from heating to cooling preference modes requires no valving and can even be done remotely. Okay, materials have been improved. Controls are important, but high-grade materials have been included because of the lithium bromide effect, and when combined with air is very corrosive to traditional materials. We'll look at each section of this. The high temperature generator is probably the most critical element. It sees the hottest temperatures and also has high concentrations of lithium bromide. This section is manufactured out of stainless steel, which can ensure a 20 to 30 year design life. And so that's pretty good. A little on the expensive side, but still good. The absorber and low temperature generator sees lithium bromide, but not as severe conditions, high temperature. As the generator, these sections are provided with copper nickel tubes to protect them from the lithium bromide, and evaporator and condenser sections see only water, so standard copper tubes are adequate there. Okay, other features with all the environmental interest today, some other features that have been added. You can get low NOx burners. And so to reduce the emission of oxides of nitrogen from the combustion of the natural gas, Trane provides them as a standard. And again, the Trane burner has an 8-to-1 turn down. It gets you down to 12% operation, which is pretty good. The Trane unit is also developed to be modular, so it can be broken down into several major components to make it easier to move and retrofit. Let's see, and the automatic purge is another feature that eliminates many of the past maintenance concerns. The purge is fully automatic, no manual operation is required. So we'll go on to the next slide here. So, okay, so now we have a number of printouts. I think these are from, this must be from a real unit. That's just not a simulation. So let's take a look at this. So what they've done is they've given the chiller some sort of a difficult change of one of the inputs, or something's happened, and then they look and see how the automatic controls respond to it. So this one is they injected a bunch of nitrogen into the absorber, Okay, so this shows how the automatic purge operates in a real life situation. So at the 40-minute mark, 6 liters of nitrogen were added or injected into the absorber section of the unit to simulate a leak. Okay, under these circumstances, the unit operated as suspected. Capacity drops rapidly. Okay, so here's capacity. So we were up here. We inject this stuff and capacity bottoms pretty quickly. And leaving water temperature rises. So here's the actual leaving water temperature. We were down here on set point, and you see we went up and we stay up for a while. Significant to note is the burner firing rate. So in the past, what would happen with typical manual purge, the response of the machine would be to increase burner firing rate because the unit's losing capacity. Increasing the firing rate under this condition will probably either crystallize the machine or shut the machine down because of impending crystallization. With an automatic purge that communicates with the controls, burner firing rate actually decreases because the machine realizes it's had a leak. And so instead of increasing burner firing rate and keeping it high, it drops it back because it realizes that it could well crystallize. Okay, so you see over a period of a few hours, the nitrogen is purged from the machine. The unit gradually goes back down to design, design capacity. So say we decrease burner firing rate, and then eventually we work back up to full capacity on the machine. We don't have much of an excursion in the chill water. It goes up a little bit, and so it's pretty good. Big advantage of the automatic purge gives you is that the air is taken out of the machine almost immediately after it enters before it can cause any long-term damage. Purge also communicates with the controller so that if a leak does occur, the controller will alert the user through the control panel. So pretty good. Okay, so that's the purge controls. Now let's see what happens if we start jerking the condenser water temperature around. So let's take a look at this one. So this one shows how the horizon machine will react to a change in cooling tower temperature. In the past, absorbers have had difficulty with cooling tower fluctuations as small as 10 or 20 degrees. Here, they're going to take the cooling tower, they're going to run it at 105, and then they're going to drop it to 55. Whoa, what is that, a 50-degree change in a period of 20 minutes? Absorbers in the past would never have been able to operate at 105 to start with, or 55, much less to take this kind of a drop in a short period of time. So at the 10-minute point, the most drastic drop in condenser water, the machine actually shuts itself down due to risk of crystallization. So here's our drop. Well, they didn't get all the way down to 55. I guess eventually we got down to 55 about here. But anyway, this is a big drop, and the machine goes, whoa, Nelly, and shuts itself down. The unit automatically reset itself, and in a matter of about 6 minutes, absorber regained control of leaving water temperature. So we do get, here's our leaving water temperature. We do get a spike, but it comes back down, and they're saying about 6 minutes before we got control of it. You may also notice the ramping of the chill water, the set point, the yellow line. I'm sorry, so this is the, let's see. Yeah, the yellow is the set point. So this was the actual evaporator temperature here. Okay. So the yellow shows that it actually changed the set point when it restarted itself. It got itself back kind of in proper operation. This is due to soft starting feature of the controls, which ensures the unit will not ramp up too quickly during startup. So anyway. you can read over that. Okay, here's one. They call this a real life scenario where condenser water temperature kind of seesaws up and down. And basically you can see that the chill water temperature was, the set point is the yellow, and the kind of magenta one is the actual. I mean, it got a little bit of fluctuation, but it's not too bad. And also notice that it's set on 39 degrees, which is pretty darn low for an absorber. So that's pretty good. This one shows, so these days in chill water system design, in order to save pumping energy, they've developed a concept called variable evaporator flow. In the old days, the rule of thumb was you didn't or couldn't or shouldn't vary the flow through the evaporator. That's where the refrigeration effect was actually going to happen. These days, it's pretty standard stuff, and you can reduce some pumping energy by doing it. And so they're showing the ability here to do this on an absorber and a variable evaporator flow. So in the past they couldn't do it, etc. So what they're talking about, I mean, there's all kinds of drops on here, but here's a big one from 1400 down to 600. We'll cut it more than in half, and you can see the variation in chill water leaving temperature is very, very small. So it handles it pretty well, which is pretty impressive. Okay, let's see, some system issues, hybrid plants used for peak shaving, and emergency cooling on power loss. We don't need hardly any electrical, a little bit to run pumps. So if you're on an emergency generator with limited capacity, the absorber is much easier to keep online. Let's see. Such a hospital would be an example of that, so very little. Low cooling tower flow is another benefit we're seeing in the large chill water plants. For example, we find that when we reduce train direct fire absorption from 4.5, which is a standard condenser water flow, GPM per ton, to 3.6, we only lose about 1% of capacity and efficiency. So that may be worth doing. But, so they can reduce the pump size and tower flow and all that. Okay, so, and they mentioned that this lower GPM capability, if you're going to retrofit, you've already got pipes in, and the pipes weren't sized for the 4.5 GPM per ton, but you may be able to cram 3.6 because they were probably designed for 3.0. So anyway, lots of good information. Okay, so that's the end of this one. Hope you enjoyed it, and I'll be posting more in a little while. Have a great day.